Melting points, performing an analysis. In this webcast, we will discuss how to perform a melting point analysis and what we can learn from performing a melting point analysis. The first thing you will do is acquire a melting point capillary tube. This tube is a small glass rod where one end, the bottom, is sealed and the other end, the top, is open. You will take this capillary tube and press the open end into a small amount of your solid sample. This sample uses a watch glass because the glass is a hard surface, although you could also do this in a weighing boat or other soft surface. By tapping your capillary tube into the solid, you will push some of your solid into the capillary tube. You will then flip your capillary tube the right side up and tap the bottom of the tube onto a hard surface, such as your bench top, to cause your solid to move to the bottom of the tube. The amount of material in a capillary tube should actually be quite small. You're looking for a height of about 1 to 2 millimeters. If you pack too little into your capillary tube, you might miss it melting. If you pack too much in a capillary tube, you will get inconsistent heating and therefore a bad melting point. Once you have your sample ready, you will then take your capillary tube and place it into the Mel-Temp here. The Mel-Temp you will use may look different than this one, but they all work the same way. You can view your sample via this magnifying lens here. You control the rate of heating using this knob down at the bottom, and you read the temperature inside the Mel-Temp via this readout here. A note about this knob: these numbers you see do not correspond to particular temperatures. In the Mel-Temp area, there are small cards that show how particular power settings correspond to particular rates of heating and particular max temperatures. You can use those cards as a reference to determine how high to set your power setting. Okay, so you've prepped your sample, it's in the Mel-Temp, and you have begun heating your sample. What should you expect to see? Here on the left, we have a sample that is just beginning to melt. We see a very small amount of liquid begin to form. When you see this happen, record the temperature at which this is occurring. This is the start of your melting range. Over time, as you continue to heat, your solid will eventually turn completely into a liquid. The moment it turns completely into a liquid, record that temperature. That is the end of your melting range. For accurate melting points, you must heat carefully. If you heat too quickly, you 1. Might miss your sample melting altogether, or 2. Record values that are incorrect. You should be looking at an increase in temperature of about 1 to 2 degrees Celsius a minute. Some tips before you get into the lab. The melting point will always be reported as a range. Remember, the beginning of the range is when you first begin to see liquid, and the end of the range is when your sample is completely liquid. Do not melt your sample too quickly. You're looking for, ideally, a 1 to 2 degrees Celsius per minute change. Allow your Mel-Temp to cool between melting point analyses. You do not want to put your sample in when the Mel-Temp is already above the melting point temperature of your sample. Be aware and watch your sample to avoid having to repeat your melting point analysis. Watching a solid melt is admittedly not the most exciting thing, but you still must watch it to ensure you record accurate data. Depending on how the Mel-Temp is set up, it might be possible to fit more than one capillary tube in a single Mel-Temp. Ask your TA for advice. Finally, make sure your sample is dry. Any solvent that is still clinging to your solid sample will act as an impurity and lower the melting point of your sample. Now we're going to discuss the uses of performing a melting point analysis. A melting point analysis can allow us to learn 2 things about a sample. It allows us to probe the purity of a known solid substance. It also allows us to determine the identity of an unknown solid, assuming I have corroborating evidence from other sources. How can a melting point analysis allow us to learn something about the purity of a sample? Remember, the presence of impurities will lower the melting point of a compound. On this slide, I have 3 samples of benzoic acid, and I've listed their melting points below the images. Pause the video and take a minute to think about which of these is the most pure and which of these is the least pure. Welcome back. I know that the presence of an impurity will lower the melting point of a sample. That means that the sample with the highest melting point should be the most pure. As we can see, the sample in the middle has the highest melting point of the three possibilities. Therefore, this middle sample must be the most pure. What about least pure? Well, we also know that the more impure a sample is, the lower its melting point, and the wider its melting point range. Look at the sample on the right, we see that the melting point is the lowest of the three possibilities, and the melting point range, which here is 4 degrees Celsius, is wider than the other two. Therefore, sample 3 must be the least pure of these possibilities. How can we use melting points to establish the identity of a compound? To do this, we will use a particular technique. On this slide, we have 3 samples, A, B, and C. One of these vials contains meta-nitrophenylacetic acid. The other 2 vials contain benzoic acid. Meta-nitrophenylacetic acid and benzoic acid have the same melting point, 120 to 122 degrees Celsius. This is important. These are different compounds that possess the same melting point. Therefore, we can't melt them individually to figure out which vial contains the meta-nitrophenylacetic acid. What we can do is perform a mixed melting point analysis. We know that impurities will lower the melting point of a compound. How can we use this? Well, let's say we mixed vial A with vial B. If they are the same compound, then there should be no change in melting point. If they are different compounds, we should see a depression in melting point. Let's look at these results on the right. Mixing A with B gives a melting point of 120 to 122 degrees Celsius. Mixing B with C gives us a melting point of 112 to 118 degrees Celsius. This mixed melting point is lower than the mixed melting point for A and B. Interesting. Let's look at A and C. Mixing these 2 compounds results in the melting point of 110 to 117 degrees Celsius. What this tells me is that A and B are the same compound because we don't see a depression in the melting point. In contrast, B and C are different compounds because we have a lower melting point. A and C are different compounds for the same reason. Therefore, vial C must be meta-nitrophenylacetic acid. These compounds all have the same melting point, but we still see a melting point depression for mixing B with C and mixing A with C because the 2 mixed samples were not the same compound. That brings us to the end of this webcast. To recap, melting point analysis samples should be the appropriate height, 1 or 2 millimeters, and heated carefully. A melting point analysis can be used to establish the purity of a compound. Pure compounds have a narrow melting point range. Melting points can also be used to identify a compound via what is called a mixed melting point experiment. If you take an unknown compound and mix it with a known compound and you do not see a melting point depression, that means the 2 samples must be identical.